Hello students, welcome to the amazing platform of PW English. So my dear students, today we are on the lecture 5 of solutions chapter, my dear students. In the last lecture, we actually discussed about Raoult's law. What is Raoult's law? We studied about how can we differentiate between volatile compounds and non-volatile compounds. Now we are going to take this discussion a little more further. Now we know that what is Raoult's law, right? Yes. Today we are going to study about ideal solutions. What are ideal solutions? What if a solution doesn't follow Raoult's law? We'll discuss everything about all these types of solutions. So now let us start the amazing session. So if we talk about what are we going to cover today, we are going to cover ideal and non-ideal solutions. Then we will be covering azeotropes, and then we will be doing practice questions as well as a lot of previous year questions also. Let me tell you, my dear students, now the part has came where a lot of the PYQs are actually based on. So you have to focus on each and every part because every part is very scoring. So let's start the discussion. Now, I hope all of you remember, just a second, yeah. So now I hope all of you remember that when we talked about Raoult's law, actually ma'am gave you a case, right? Yes, we studied about a case, and in that case we told that what if solute as well as solvent both are volatile. So now let's discuss a second case. First we will discuss about the second case of Raoult's law. What is the second case? Let me just tell you. Let's talk about the second. Let's talk about the case 2. So what does case 2 tell you? That what if one of the component is non-volatile, and more preferably the solute is non-volatile. So your second case will be when solvent is volatile and solute is non-volatile. So now we will study about what if a solvent is volatile in a solution but your solute is non-volatile. How we can calculate the vapor pressure of that particular solution. So now, my dear students, if this is the case, we can say that ma'am, if the solvent is volatile, let us call solvent as 1 and solute as 2. Okay, so if solvent is volatile, then we can say that P1 naught will not be equal to 0 because ma'am, it is volatile, it will form vapors, right? Yes, and the solute is non-volatile. Now, my dear students, if your solute is non-volatile, means that it will not form vapors, and if it is not forming vapors, then ma'am, it will not have vapor pressure. So the vapor pressure of the pure component will be equal to 0. So this will be equal to 0. I hope this is clear. No issue still here. Perfect. Now what are we going to do? Now we are actually going to apply the Raoult's law. Okay, the same way we applied the Raoult's law in the case 1, we'll apply in the case 2, and you'll understand each and everything very clearly. Okay, now imagine you have a closed container, and you have a solution here. Now, my dear students, let me represent the solute components. The solute is non-volatile, right? Yes. So the solute will be present here in the bulk as well as it will be present on the surface too, right? Perfect. Now, what you need to understand here is that, my dear students, imagine that initially if you had a pure solvent, right? Yes, then the pure solvent vapor pressure would be P1 naught, right? Pure solvents vapor pressure would be P1 naught. You added some non-volatile solute to it. You know that non-volatile solute vapor pressure, which is P2 naught, this will be equal to 0. I hope this is clear with you. Now, this is your solution, and I know that PS is the vapor pressure of the solution. So vapor pressure of solution is given by PS, right? Yes. If pure solvents vapor pressure is P1 naught, if non-volatile solutes vapor pressure is P2 naught, my dear students, and your solution is here. So according to Raoult's law, we know that according to Raoult's law, we know that solution is equal to P1 plus P2. These are the partial vapor pressures, right? Yes. Now, if we open these partial pressures, we can write the formula as P1 naught mole fraction plus P2 naught mole fraction of your solute. Here, my dear students, we can say that X1 and X2 are mole fractions of solute and solvent. Just a second, solvent and solute. Okay, this will be X2 and X1 are the mole fractions of solute and solvent respectively, right? I hope this is clear with you. The mole fraction here would be X1 and the mole fraction here would be X2, right? Yes, it is a non-volatile solute, but it will have some mole fraction, right? Yes, and also we know that X1 plus X2 is equal to 1, right? Clear? Now, you know that this is equal to this expression. Now, just put the values which you know here. P1 naught into X1, okay ma'am, we will have some P1 naught value, it is not equal to 0, and we will have some mole fraction as well. So, the solution PS will be equal to P1 naught X1 plus P2 naught value is 0, my dear students, because it is a non-volatile solute. It will not have any pure vapor, pure solute will not have any vapor pressure. So this will be X0 into X2. So from here we can say that P of solution is equal to P1 naught X1. We can say that it is equal to P1 naught X1, right? Yes. So now imagine you have PS equal to P1 X1. See, the vapor pressure of the solution came out to be, just a second my dear students, just a second. Okay, now let's start what I said. I told you that the vapor pressure of the solution, has came out to be P1x1, right? Yes. Now, my dear students, we now very clearly understood that if a non-volatile solute is added into a solution, then the vapor pressure of the solution comes out to be P1 naught x1, right? Yes. Now, this is clear. We don't have any issue with it. Now, my dear students, I just want to ask you one simple question. If you have understood this concept, then you can answer this question. And if you were able to answer, then congratulations, the concept is clear. So, the question is, P1 naught is the vapor pressure of pure solvent, and PS is the vapor pressure of solution. Which of the following is higher? Now, you have to tell me that out of P1 naught and PS, which vapor pressure is higher? Okay, so now let's imagine we can answer this question in two different ways. We can answer it mathematically and we can answer it conceptually as well. Okay, so we'll answer this. Okay, now first, my dear students, imagine you know that PS is actually equal to P1 naught x1, where what is x1 is the mole fraction of solvent, right? Yes, if x1 is the mole fraction of solvent, then my dear students, we know that x1 plus x2 is equal to 1, where x2 is the mole fraction of your solute, right? Yes. Though your solute is a non-volatile solute, it cannot have any vapor pressure, but it will have some mole fraction. Yes, ma'am. So can I say that from here I can see that x1 will always be less than 1. X1 will always be less than 1. It cannot be equal to 1, because if it is equal to 1 means that it is a pure solution. So always and always x1 is less than 1. Okay. If your x1 value is less, then PS is equal to P1 naught into x1, my dear students. Now imagine x1 is less than 1. Right, x1 is less than 1. This means that if your x1 was equal to 1, then the solution's vapor pressure would have been P1 naught, that is total equal to P1 naught. But if P1 is multiplied by some fraction, imagine you multiplied 2 by some fraction, let's say 0.1, then your value will come out to be 0.2. Yes, if you multiply a whole number 2 by, let's say, 0.9, which is again less than 1, again this value will be 1.8, again less than, the value will be less than 2. So any whole number multiplied by a fraction will give you a smaller number, right? Yes. So from here I can say that since x1 is less than 1, always and always PS will be less than P1 naught. PS will always and always be less than 0. P1 naught, right? Yes. So from here I can say that always and always, whenever you will add a non-volatile solute into a solvent, the vapor pressure of the solution will be less than the pure vapor pressure of that particular solvent. Okay, this was how we explained mathematically. Now let's understand it conceptually. Imagine, my dear students, you had this container. Imagine you had this container. Just a second, I'll show you on this page. Yeah. You have one container here and you have one container here. You have the same type of container. In one container, you have only solvent. This is your pure solvent. If you have a pure solvent, then you can say that the vapor pressure here will be P1 naught. Okay. Now you have the same solvent here and you added some non-volatile solute to it. Now you have added some non-volatile solute to it, right? Yes, it will be in bulk, it will be on surface. So here the vapor pressure of the solution will be PS, right? Now imagine how vapor pressure depends on temperature. You will keep on heating the containers, you will keep on heating this container, what will happen? Vapors will form, and at one particular point you will find out that the total what is the maximum vapor pressure, right? Yeah. Now, if this solvent, you see, all the surface is available for the particles to go into the vapor form, right? Whereas in the case of solution, here, see this non-volatile solute, the non-volatile solute has covered some surface of the solvent and it is hindering the particles to form vapors faster. So more vapors will be formed here at the same temperature compared to this. So we can say that the vapor pressure for your solvent will always be more than the vapor pressure of your solution at a particular temperature T, as long as you keep the temperature T, because you increase the temperature. As you increase the temperature, vapors will increase here as well as here, but the amount of vapors forming here will be more as compared to the vapors forming here, because the non-volatile solute is hindering some surface as well. So this is how we understand conceptually that why the vapor pressure of the solution is always less. Okay, I hope it is clear with you. Now let's move forward. Now, my dear students, next thing which we need to understand is boiling point. I need boiling point. I want to make you understand the concept, the major concept between of the boiling point. What is boiling point? How do you define boiling point? You might have heard this definition a lot of times. Today you will actually understand this. For any solvent solution, any solute or solvent which is volatile, how do you calculate its boiling point? What is the boiling point? It is a temperature. Okay, yeah. So what is boiling point for a solvent or a solution? Boiling point is the temperature. Boiling point is the temperature at which the vapor pressure inside the container, becomes equal. Let's say here you have atmospheric pressure, becomes equal to the atmospheric pressure outside, which this means that you keep on heating the container, the solvent will form vapors, and the vapor pressure will keep on increasing. There will be a particular temperature where the vapor pressure inside the container will be equal to the outside atmospheric pressure, and that particular temperature for that particular solvent or solution is known as its boiling point, right? Yes. So we can say that it is the temperature at which the vapor pressure of a volatile component becomes equal to the atmospheric pressure. Okay, this is how you define boiling point. Okay, I hope you're clear with this concept. Now, my dear students, imagine you have two different components. I'll just give you an example. You have component 1 and you have component 2. Let's say its vapor pressure is P1 naught and its vapor pressure is P2 naught. Okay, yes. Let's say boiling point of this is BP1 and this is BP2. I am telling you that if P1 naught is more than P2 naught, if P1 naught is more than P2 naught at a particular temperature, my dear students, then tell me which of the following components will have a higher boiling point. Which of the following will have a higher boiling point? Right? Yes. So now let's understand this. If I know that component 1 vapor pressure is more than the component's 2 vapor pressure, I can say that. What can I say? I can say that component 1 is more volatile because at the same temperature it has more of the vapor pressure, which means that it has formed more of the vapors, right? Yes. So ma'am, component 1 is more volatile. Now I need to find out which has a higher boiling point. Imagine, my dear students, if a component can form more of the vapors at a particular temperature, then the tendency of it that the inside vapor pressure will be equal to the atmospheric pressure will be faster for the one which has a higher vapor pressure. The more the vapor pressure, the easier it will be equal to the atmospheric pressure. At a low temperature, the vapor pressure will be equal to the atmospheric pressure, right? Yes. So I can say that if component 1 is more volatile, it has more vapor pressure, then at a lower temperature its vapor pressure will be equal to the atmospheric pressure, whereas component 2 will need more of the temperature to form more of the vapor so that it could be equal to the atmospheric pressure. Right? So which of the following will have a higher boiling point? Component 2 will have a higher boiling point. So you will say that component 2 will have higher boiling point. Okay, so from here we have deduced a very important relation, that if a component is very volatile, then it will have a lesser boiling point. So we can say that volatility of any component is inversely proportional to its boiling point. Volatility of any component is inversely proportional to its boiling point. The more the volatility, the more the vapor pressure, the lesser will be the boiling point, right? Yes, so I hope you're clear with this concept, my dear students. You can just go through each and every part and then we'll move forward. So this was our case 2, where we discussed that we had solute as non-volatile and solvent as volatile. We found out the solution's vapor pressure. Then we found out that solution's vapor pressure will always be less than the vapor pressure of the pure solvent. We understood it mathematically as well as conceptually. Okay, perfect. And then, my dear students, we compared that if we have two different components and if one is more volatile, then which will have a higher boiling point. Okay, perfect. I hope it is clear with you. Now let's move forward. So this was the second case and you are thorough with the second case. I hope you don't have any problem. If you're clear with the concept, congratulations, you are perfectly clear with every part. Okay, now let's move forward. What are we going to discuss now? Now we are going to discuss about ideal solutions. What are ideal solutions? See, we know solutions. Now we will understand what are ideal solutions. Okay, how are we going to understand ideal solutions? You might have heard about the word ideal gas, right? Yes, so I'll relate ideal solution to that and then you'll understand everything. Okay, so for that we need to now, when I talk about ideal gas, what we used to say, and here I'll write ideal solution. So, now my dear students, what was an ideal gas? An ideal gas was a gas which used to follow PV is equal to nRT equation at all the temperatures and pressures. A gas which can follow the ideal gas equation PV is equal to nRT at every temperature and pressure is known as the ideal gas. So a gas which follows PV is equal to nRT at all temperatures and pressures, right? Perfect, no issue. If I talk about an ideal solution, it is something same only. A solution which can follow Raoult's law at all concentrations is known as an ideal solution. So easy definition, yeah, a solution that follows Raoult's law at all concentrations, okay, is known as the ideal solution. Now, what other thing do we know about ideal gas? That in reality no ideal gas exists. There is no ideal gas in real life. There are only real gases, right? Yes, so no ideal gas exists in reality. Similarly, there is no ideal solution. It is just a theoretical concept. There is no ideal solution in reality. So, there is no ideal solution in real. Okay. Now, how can we, my dear students, make a gas behave ideally? There are some conditions you can do with which you can make a real gas behave ideally. If you take a very low pressure and very high temperature. So we used to say that at high temperature and low pressure, at high temperature and low pressure, a real gas behaves ideally. Okay. Similarly, you can say for an ideal solution that if you want to make some solution to behave ideally, then you have to take its dilute solution. You have to dilute it. That is, you should have a lot of solvent and a very small amount of solute, right? Yes. So we can say that a solution behaves ideally at very high dilution. If you dilute the solution to a very large extent, it can behave ideally. So this is how you can understand an ideal solution. How can you make a real solution behave ideally? Is this that you can dilute it to a very large extent, you can make its concentration very less, and then it will behave ideally. Okay, so you can write this and then we'll move forward. Okay, I hope you've written this. Now let's move forward. Now, my dear students, here are some what I told you. There are definitions here. You can write these definitions on your own. A solution that obeys the Raoult's law at any composition is known as the ideal solution. At any composition means at any concentration, it is known as ideal solution. No real solution is ideal. No real solution is actually ideal. You can make a real solution behave ideally by dilution. A real solution at a very high dilution can behave ideally, right? Yes. So you can write this and then we'll move forward. Okay, if the molecular, okay, now we are going to talk about the thermodynamic terms about real solution. I am going to, about ideal solution. Now, my dear students, this part is very important. A lot of questions are asked, so you have to be very attentive right now. Okay, we are going to talk about the thermodynamic parameters of an ideal solution, and then we will talk about the real solutions as well. Okay, so how are we going to discuss about ideal solution? See, a solution is made if you have two components. Let us say you have AA component. Let us say you have AA component and you have BB component, and you mixed both of them and you got AB solution, right? Yeah. Now, I am going to make you understand everything right now, and then everything will be very clear. Okay. So, first of all, you know that AA will have some force of interaction between them, BB will have some force of interactions between them, and AB will definitely have some force of interaction. So, the whole theory of ideal solutions and non-ideal solutions actually depends on the force of attractions between them. So, if you are clear with this, you can understand everything. Okay. So, now, what happens? You have AA and BB interactions. So, if, my dear students, AA interactions are equal to the BB interactions, okay, if these interactions are similar to these interactions, then they both will mix, and the interactions here will also be similar. So, this means that for an ideal solution, AA interactions should be equal to BB interactions, and they should be equal to AB interactions. So, the first and the most important thing for an ideal solution is that the interactions between the solute, solvent and the solution should be similar. Only then they can behave ideally. If the interactions are different before the solution, before the mixing of the solution and after the formation of the solution, then it will not behave ideally. Okay, yes. So, if the molecular interactions before and after mixing remains the same, the solution will be an ideal solution. This is the most important case. If you're clear with this, then everything is clear. Okay, now we are going to talk about three basic thermodynamic parameters. Okay, now let's talk about the parameters. The first parameter is delta H, mixing. That is the enthalpy of mixing. How are you going to understand this? Very easy, my dear students. You know that when you mix AA with BB, you get 2AB. You get 2AB. Okay. Now, you know that for a solution for a solution to form, the solute-solute interactions, the solvent-solvent interactions need to be broken, right? You need to break this interaction, only then AB interaction will be formed, right? Yes. Whenever a bond is broken, whenever a bond or an interaction is broken, you need to provide energy to it. Write it in your mind, my dear students, that whenever a bond is broken, or an interaction is broken, you need to provide energy. So you will provide some energy here. So this will be in a positive value. And whenever a new interaction is formed or a new bond is formed, always and always energy is released. So here, my dear students, energy is released because a new bond, a new interaction is formed. And when energy is released, its value is always negative. Okay, yes. I hope this is clear. Now let's discuss. Now let's understand. I know that to break a bond, I need to give energy, right? That would be a positive value. To form an interaction, it will release some energy, that will be in negative value. Now, my dear students, for an ideal solution, we know that AA interaction is equal to BB interaction and it is equal to AB interactions, right? Yes. So let us say that 2 plus 2 joules of energy was absorbed to break this bond. Now, plus 2 joules of energy was absorbed to break this interaction as well. Then, minus 4 joules of energy will be released when 2 AB interactions will be formed. Why? Because all the interactions were similar, and that is the reason that how much energy was absorbed, equal energy was released. So if you see, overall delta H of mixing will be equal to 0. So overall delta H mixing came out to be 0 for an ideal solution. Since the interactions are equal energy is absorbed for breaking the interactions and equal energy is released when a new interaction is formed. And that is the reason delta H mixing is equal to 0. So you can see the energy absorbed when solvent-solvent bonds and solute-solute bonds are broken is exactly equal to the energy released when solute-solvent bonds are formed, right? Yes. So you can write this and then we'll move forward. I hope you've written it. Now let's move forward, my dear students. See. Now we will talk about delta V mixing. If we are talking about delta V mixing, this means that we are calculating the change in volume difference. Okay. So now imagine you had solute here, AA. You had solvent here, BB, and you got a solution 2AB. Okay. Now, my dear students, if the interactions are same, we know that AA interactions are equal to BB interactions are equal to AB interactions. So if the interactions are same, molecules will have same interaction, they will be equally spaced. Okay. So if the volume here is 2 liters and here also the volume is 2 liters, then the total volume here will be 4 liters because the interactions are same, right? Yes. So if you find delta V mixing, that is volume final minus volume initial, it will be 4 minus 4, which is equal to 0. Yes, that is the reason delta V mixing is also equal to 0 for an ideal solution. The reason is it has the same equal interactions. Okay. See, since the intermolecular attractions doesn't change after mixing, volume remains the same. Okay. I hope this is clear. You can write this and then we'll move forward. Let's move forward. Now, okay, delta V mixing is done. Now, let's talk about delta S mixing. What is delta S mixing, my dear students? It is the entropy change. What is entropy change? Entropy actually measures your randomness. You might have studied this concept in the thermodynamics part. Entropy change is actually randomness. Entropy change is actually randomness. That is the measure of randomness. Okay. Now, imagine, my dear students, imagine you have these balls in one container, you have these balls in one container, and you have these balls in another container. Now, if you have white balls in one container, okay, and I ask you that this is a container which contains white balls, just put your hand in it and bring and take out a ball and just let me know what give me the probability of colors you can find out. You will say, obviously ma'am, it will be a white ball because this container contains the white balls. So is there any randomness present? No. If I talk about this container, I tell you that take out a ball out of it and just let me know that what will be the color. You will be like, ma'am, yellow color, because all the balls are yellow color. Is there any randomness? No. But once you mix these two, now you have a container where there are two different types of balls, yellow and white. Now if I ask you that, now tell me the probability of taking out a ball, you will say, ma'am, it can be white, it can be yellow, right? Yes. This means that there is randomness this time, right? Yes. So my dear students, you had randomness here, that is your final case, but you didn't have any randomness in the starting. So always we know that the change in randomness, that is delta S mixing, will always be a positive value, right? Yes. So this will always be positive because in the solution you have randomness, but in the solute and solvent part you didn't have randomness, right? Yes. So now let's read this. In solution we have two different types of particles, and the entropy, the solution is always higher than the pure solvent and pure solute. If you want to write, you can write that entropy is the measure of randomness. Measure of randomness. Okay. So this is how you will understand the randomness part. I hope this is clear with you. You can write this and then we'll move forward. Let me have some water. So there are three thermodynamic parameters which we have studied till now. Okay, I hope this is clear with you. Okay, perfect. Now let's move forward, my dear students. Just let me see if it is getting recorded. Yes. Okay, perfect. Everything is on place. Let's move forward. Now, my dear students, I hope you've written this. I'll give you some time to write also. You can write this part. Then you can write this part. Then you can write this part. Okay. Now, my dear students, ideal solution mixing is a spontaneous process and it is an entropy effect. This is how you define a ideal solution. How do you define an ideal solution? Ideal solution is a solution, and ideal solution is a solution which ideal mixing is a spontaneous process. Why is it a spontaneous process, my dear students? I can make you explain this as well. Imagine you might have studied in your thermodynamics. In your thermodynamics, you might have studied a expression which is given by delta G is equal to delta H minus T delta S. Okay, this is the expression that you have studied. Okay, also, my dear students, I hope all of you remember, for a reaction to be spontaneous, if your delta G is negative, your reaction is spontaneous. Right? Yes. And if your delta G is a positive value, it is a non-spontaneous process. It is a non-spontaneous process. Okay. Now, you have just studied the thermodynamics parameters. Can you apply those parameters in this equation and find out if it is a spontaneous process or not? Yes. See, for ideal solution, I know that delta H is always 0. I'll write it as delta H mixing is always 0. Right? Yes. And I also know that delta S mixing is always a positive value. It is always the positive value. Right? Yes. If you put these two values in this expression, what will you get? You will get that delta G mixing is equal to 0 minus T delta S, and delta S is always a positive value. Since this is a positive value, can you say that this whole part will be positive? And since there is a negative sign, I can say that this whole part will always be negative. Now, since your delta G mixing is always coming out to be a negative value, because temperature cannot be negative, my dear students. T is the temperature, and temperature can never be negative. It will always have a positive value. So, ma'am, this whole part will always be a negative value. So, delta G will always be negative for an ideal solution. So, it is a spontaneous process. That is the reason it has said that ideal mixing is a spontaneous process, and it is an entropy effect. Why is the entropy effect? Because in mixing of solutions, always and always entropy is the positive value. Delta S mixing, entropy is positive. That is the reason it has said these two different parts. I hope you're clear with this. Yes, so you can write this and then we'll move forward. Okay, now since you are clear with the ideal solution, now we are going to plot some graphs for ideal solutions. Okay, so vapor pressure and mole fraction of ideal solution. So now we are going to plot a graph for vapor pressure and mole fraction of ideal solutions. Okay, now first and the most important thing, my dear students, what are we going to do? I am telling you that PS, your solution will be equal to P1 plus P2. I can say that PS will be equal to P1 naught X1 plus P2 naught X2. Where, my dear students, X1 and X2 both are volatile. At this point, we are considering the first case where your both components are volatile. Okay, if both are volatile, then this means that this expression is absolutely correct. Also, I am telling you that component 1 is more volatile. Okay, I have told you this, that component 1 is more volatile. Now you have to plot a graph. Okay, so now my dear students, if you need to plot a graph, what will you do? Imagine you have this x-axis, y-axis. Okay, now first we are going to talk about P1 naught x1, which is equal to P1 part. Okay, yes, so what can I say here? I can say this will be x1 and this will be P1, partial pressures, because it is a mixture of two components. Okay, now you can say that, ma'am, you can say that with the increase in the mole fraction, you know that from the Raoult's law, you know that P1 is directly proportional to the mole fraction of that component in the liquid phase. The more the mole fraction of that component in the solution, the more will be its vapor pressure, right? Yes. So I can say that as we increase the mole fraction, the same way the vapor pressure will increase. Right, there will be a point, let us say at this point where mole fraction x1 is equal to 1, then the corresponding vapor pressure to this will be P1 naught, and when the mole fraction is equal to 1 means that you have only one component present there, which is your first component, right? Yes. Now, if you have drawn this, can you draw the same expression, same graph for the second component? Yes, ma'am, we can draw. See, you have x2 here, you have P2 here. Same, my dear students, you know that P2 is directly proportional to x1. 2. P2 is directly proportional to x2. So you can say that P2 will be equal to P2 naught x2, right? The more the mole fraction of the second component in the solution, the more will be its vapor pressure. So the plot will be something like this. There will be a point when x2 will be equal to 1. If x2 is equal to 1, this means that the whole of the component is only the second component, that means pure component. So the corresponding vapor pressure will be P2 naught, right? You have understood this part. If I ask you to plot a graph for both of them together, how can you plot that? Let's plot that graph now, my dear students. Imagine you have something like this. Okay. Okay. Now, what are we going to do? Now we are going to plot the graph. How are we going to plot the graph? See, I told you on the x-axis you need to write the mole fractions, and you know that there are two components, which means that x1 plus x2 is equal to 1. x1 plus x2 is equal to 1, right? Yes. So imagine if I say here x1 is equal to 1, then I will definitely have to say that mole fraction of second component is 0. Right? Yes. If the mole fraction is equal to 1 for first component, then here, my dear students, on this axis, the vapor pressure will be of pure component A, because mole fraction of 1 is shown to be completely equal to 1. So pure component, right? Yes. So I know that here the vapor pressure will be for P1. And since this is P1, and my dear students, similarly, as we go this side, the mole fraction of 1 will keep on decreasing. Let's say here the mole fraction of 1 is equal to half. Then the mole fraction of 2 will also be equal to half. Right? Yes. Then at this side, as we move, the mole fraction of 1 will keep on decreasing and the mole fraction of the second component will keep on increasing. Here, mole fraction of 1 will be equal to 0 and the mole fraction of second component will come out to be 1. Since here the mole fraction is completely because of 2, here the complete mole fraction is because of 2, so the vapor pressure which will here it will come out to be for P2 naught, okay, and here it will come out to be P1 naught. Now my question to you is out of P1 naught and P2 naught, which will be higher? I gave you a hint here that component 1 is more volatile. If component 1 is more volatile, this means that component 1's vapor pressure will be more at a particular temperature T as compared to the second. So P1 naught will be a little higher and P2 naught will be a little lower than P1 naught. Okay. Yes. Then what do? Then we join these two. If I join this, what am I showing here? See, my dear students, what am I showing here? I am showing here that as I am increasing the mole fraction of second part, the second component's mole fraction, initially here it was 0, so it doesn't have any vapor pressure. As we increase the mole fraction, the vapor pressure keeps on increasing, right? So, my dear students, this is how you see this part. Okay. Similarly, if you join this, what can you say? You can say that as I increase the mole fraction of 1, I get the vapor pressure of the second component. Now, if you join these two, my dear students, you actually get the vapor pressure of the solution, which is equal to P1 and P2, P1 plus P2 at any particular point. Okay, I hope this is clear with you. And the most important thing is, at this particular point where they cross each other, my dear students, this is the point where P1 pressure is actually equal to P2. That is, this is the point where the partial vapor pressures of the first and the second component are equal. This is how you read a ideal gas, This is how you read a ideal solution graph. Okay, I hope you're clear with this part. Yes, let's see this if you have made it clear. You just drew two components graph. These were easy. What you did, you just combined the two here. You only have to imagine that if first component is complete, then you will not have the second component. The vapor pressure will be because of the first component. Here, if you have all the component second, then the vapor pressure will be only because of second component. If we join these two, we get the vapor pressures, partial vapor pressures of each at different points. If I join this line, I get the total vapor pressure of the solution, that is P1 plus P2, right? Yes. So this is how you calculate the vapor pressures. This is how you plot the graph. I hope it is clear. You can pause the video and then we'll move forward. I hope you've written this. Now let's move forward, my dear students. Now we'll solve some question. Okay, so now what does the question say? The vapor pressure of liquid A and liquid B is 500 mm of Hg and 800 mm of Hg. That is, it is given the pure vapor pressure of those two components. Select the correct option at point O. Point O is not given. Okay, ma'am will draw. Actually, the plot is something like this. See, I'll draw the plot and you'll understand everything. See, you have the vapor pressure of liquid A and liquid B 500 and 800 mm of Hg, which means that you will have PB naught equal to 800 and PA naught equal to how much? 500. Okay, so you know that this will be like this and this will be something like this, and your point O is here. So you have to tell at this particular point what is actually happening. So my dear students, at this particular point, the partial pressure PA will be equal to the partial pressure PB, right? Always and always make it clear, and this is how questions are generally asked. So PA will be equal to PB. Option A will be your correct answer. It is not important that the mole fractions will be equal. No, the partial vapor pressure of two components will be equal, not the vapor pressure, not the mole fractions. Okay, make it very clear with your concept. The mole fraction can be equal here, or it could be anywhere. It is not important that it will be at this particular point. Okay, yes, perfect. I hope it is clear. Now let's move forward. Now my dear students, till now we were discussing only and only about an ideal solution. But what if I told you that ideal solution don't exist? Actually, the solutions exist are non-ideal. How are they non-ideal? I told you an ideal solution is a solution which actually obeys the Raoult's law, which means that according to the Raoult's law, the vapor pressure of the solution is equal to the partial pressure of A plus partial pressure of B. If a solution's vapor pressure comes out to be equal to, calculated according to the Raoult's law, it is known as an ideal solution. But what if it doesn't come equal to that? Then it will be a non-ideal solution. Now it can deviate from that in two different ways. Either the vapor pressure of the solution will be more than that calculated from Raoult's law, or it could be less than that calculated from the Raoult's law, right? Yes, and in that way we find out, we differentiate between the two non-ideal solutions, as one is known as positive deviation, the other as negative deviation. Now let's understand why are we calling them positive and negative deviations. If PA is equal to PA naught XA and PA is not equal to PA naught XA for real solutions. Now my dear students, for a positive deviation, the vapor pressure of the solution will be more than calculated from the ideal solution. If the vapor pressure of the solution is more than calculated from the Raoult's law, that is known as your positive deviation. And if the vapor pressure calculated of the solution comes out to be less than that calculated from the Raoult's law, it is known as a negative deviation ideal solution. Okay, now we will be studying about the thermodynamic parameters of both of them individually. Okay, yes, first my dear students, let's discuss about the examples of ideal solution. Okay, let's talk about the examples of ideal solution. Where is an ideal solution? Just a second, I'll write it here only. Okay, examples. So what are the general examples of ideal solutions? See, you need not remember all the examples, but you need to have a little bit idea about how can you see the examples and find out it will be ideal solution or not. See, I told you that all the interactions are nearly equal. So normally ideal solutions are those solutions behave ideally which have very weak van der Waal interactions. This means that, example, if you have a solution of benzene and toluene, they are nearly non-polar, they have weak van der Waal interactions and they behave ideally because their interactions are nearly equal after mixing, before mixing. Okay, so such examples which have nearly non-ideal cases, let's talk about bromoethane, not bromoethane, let's talk about ethane and methane. This will also be a ideal solution. So the solutions which are equal, which have nearly same interactions, mostly van der Waal interactions, they behave ideally. Okay, so this is how you can see the examples. Okay, now we are going to talk about first the positive deviation. See, my dear students, in positive deviation I told you that the vapor pressure of the solution comes out to be more than that calculated from the Raoult's law. Okay, yes, now imagine you know that a solution is made by AA plus BB will give you 2AB. Now in ideal solution all the interactions were equal, but since it is a non-ideal solution, then it will have different interactions before and after mixing. Okay, yes, now what is the case, which is more and which is less? You can yourself calculate it. If the vapor pressure comes out to be more than that calculated from Raoult's law, this means that after mixing the interactions became weaker. This means that after mixing interactions became weaker. Since the interactions were weaker, more of the particles got into vapor form and there was more of the vapor pressure. So for a positive deviated ideal solution, the interactions after mixing are weaker than the interactions before mixing. So if the interactions before mixing are more and after mixing the interactions come out to be weak, it will always show positive deviation from the Raoult's law. Okay, let's see. The energy absorbed to break solvent and solute bond is greater than the energy released when weaker solvent bonds are formed. From here you can say that delta H mixing will be equal. Okay, directly they've talked about delta H mixing. Okay, I hope it is clear about the interactions. Now we can talk about all the mixing part. Okay, now let's talk about delta H mixing. If the interactions after is weaker, now imagine you have AA, you have BB, and it is giving you AB interactions. You know that you need to give energies to break the bonds. So let's say you gave 2 joules of energy here, you gave 2 joules of energy here. So this is plus, this is plus. Okay, yes. Now since this interaction is weak, then less of the energy will be released. Let's say total 3 joules of energy is released. 4 joules of energy was absorbed, but 3 joules of energy is released. So can I say that delta H mixing here will always be a positive value? It will be a positive value. Plus 2 minus 3, it will give you plus 1, right? Yes. So for a positively deviated ideal solution, delta H mixing is positive. Why? Because the amount of energy absorbed is more as compared to the amount of energy released. Now you can read this. The energy absorbed to break the solvent and solute bond is greater than the energy released when the weaker solvent bond is formed, right? Yes, I hope you're clear with this. Now we can move forward. Now If the solute-solvent interactions after mixing decreases, more molecules will move into the vapor phase, contributing more of the pressure. The line which I have been emphasizing on for a so long time right now, is this. Okay, so this is the most important part which you need to understand the difference between ideal and non-ideal solutions. Okay, I hope you're clear. You can write this and then we'll move forward. I hope you've written this. Now, next is delta V mixing. Now think about delta V mixing, my dear students. What will happen? You have AA, you have BB interactions, will give you two AB interactions, and you also know that AB interactions are weaker than AA interactions or BB interactions. So now, my dear students, imagine you had 2 liters of volume here, you had 2 liters of volume here. Now, initially the interactions were stronger, so the particles were very closely interacting to each other. But after mixing, the interactions became weaker. So now the molecules can move apart from each other a little more. This means that the total volume here will be comparatively more, let us say 5 liters around. So if you see delta V mixing, V final minus V initial, this will be 5 minus 4 plus 1, which means that delta V mixing for a positively deviated part, ideal solution is always a positive value because the interactions are weaker, so volume becomes more after mixing. Volume becomes more after mixing. I hope it is clear. You can write this and then we'll move forward. Let's talk about delta S mixing. If you talk about delta S mixing, my dear students, entropy change. Ma'am, entropy change will be always positive. Why will it be positive, my dear students? Again, the same case. You have AA balls. Okay, you have AA balls here. You have A balls. You have BB balls. You have AA balls, you have BB balls here. Right? Now, if I ask you that you have to take one ball out of it, then you will say, ma'am, obviously there is only yellow balls, so no randomness here. Here also no randomness. But if you talk about the solution, then you will have one yellow ball for A and one green ball for B. Right? Yes. So here you have randomness, and that is the reason there always entropy change delta S mixing will be positive as well. So in a solution there is randomness, in a solute or a solvent there are no randomness. Right? Yes. So I hope this is clear with you. There is no issue. Can we move forward? Let's move forward, my dear students. Now you have some examples. These examples are such examples which will have strong interactions before mixing, and after mixing the interactions become weaker. Let's take an example. You have acetone, my dear students, and acetone actually has hydrogen bonding present here. It has hydrogen bonding present here, and you add a non-polar hexane into it. What will this hexane do? It will interrupt the hydrogen bonding. So initially the bonding was stronger, and after mixing the bonding became weaker, and that is the reason it is showing positive deviation. Similarly, you have a alcoholic group here, my dear students. Again, hydrogen bonding here. Cyclohexane is a non-polar component. For cyclohexane, if you add the alcohol into it, it will hinder the hydrogen bonding, and that is the reason it is an example of positive deviation. Similarly, water and alcohol individually show hydrogen bonding. Both of them show hydrogen bonding, but once they are mixed, they show a little bit of lesser hydrogen bonding, and that is the reason after mixing their interactions become weaker, and it is an example of positive deviation. If you memorize these 3 or 4 examples which I have given you, it is enough. You need not remember every formula, sorry, every example. Okay, yes, I hope you are clear with this. Now let's move forward. You can write this and then we'll move forward. You've written it. Now can we move forward? Okay, let's move forward, my dear students. Now we're going to talk about negative deviation. If you're clear with the positive deviation, negative deviation is very easy for you now. For a negative deviation, you know that the vapor pressure, haven't we drawn the graphs? We were supposed to draw the graphs as well. Okay, first, my dear students, we have to draw a graph here as well. Okay. Okay. First, we'll draw a graph for positive deviation. So, if you talk about a graph for positive deviation, what will it be? So, now, my dear students, first draw the graph which you know for the ideal solution. Okay, what is the graph? It was like this. Then you had, let us say, PA naught is more volatile. A component is more volatile than PB naught, right? Yes. Here you will have XA equal to 1 and XB equal to 0. Here you will have XA equal to 0 and XB equal to 1, right? Yes. We can join these two and this. Perfect. If the solution was an ideal solution, this was what it's supposed to have, but it doesn't have this. What will happen, my dear students? It shows positive deviation. You know that this gives you the vapor pressure of the solution, and you know that in a positively deviated ideal solution, the vapor pressure is more than that calculated from the Raoult's law. So the graph would be something like this. So this will be like this and this will be like this. Okay, so this is how you draw the plot for a positively deviated ideal solution. Now we can move forward to the negatively deviated ideal solution. You can write this and then we'll move forward. Now let's talk about a negative deviation. So now, my dear students, you know that for a negative deviation, the vapor pressure of the solution comes out to be lesser than that calculated from the Raoult's law. If the vapor pressure is lesser, this means that after mixing, the interactions become more strong. So I can say that this time AB interactions will be more than AA interactions or BB interactions Okay, perfect. Solvent solute interactions after mixing is stronger. The solvent solute interactions after mixing is stronger than the solute solute or solvent solvent interactions. Molecules in the liquid state are strongly bound. Few molecules can escape into the vapor phase, contributing to the less of the vapor pressure. This is why it is known as a negatively deviated ideal solution. Now let's talk about the thermodynamic parameters. Now you can very easily explain me what will be the sign for delta H mixing. You know that AA, BB gives you AB. You also know that this time AB interactions are more than AA interactions or BB interactions. See my dear students, if you want to break this bond, let us say you gave 2 joules of energy, and let us say here also you gave 2 joules of energy. How much energy will be released since this interaction is stronger? So more of the energy will be released, right? Yes. So my dear students, minus 5 joules of energy will be released. And if minus 5 joules of energy is released, I can say that delta H mixing is negative. Delta H mixing is a negative value, right? Yes. So this is how you calculate the enthalpy change for a negatively deviated ideal solution. I hope it is clear. Now let's move forward. Next is your delta V mixing. I hope you can give me the answer here as well. Again, ma'am, we know that this time AB interactions are stronger than AA interaction and BB interaction. So if we have AA plus BB, which gives us 2 AB interactions. And if the volume here is 2 liters and here also it is 2 liters, now the interactions are stronger. Now the particles are coming more closer to each other, then the volume will be less, right? So let us say the volume will be 3 liters. Then my dear students, delta V mixing will be equal to 3 minus 4, which is equal to minus 1, which means that negative. So delta V mixing will be negative, right? I hope you're clear with this concept again. Because the interactions were stronger, particles will come more closer to each other, contributing to a lesser volume. Okay, perfect. Let's move forward. If you talk about delta H mixing, delta S mixing, same as the previous two parts, my dear students. Since it is a solution, always a solution will have higher entropy, positive entropy, more of the randomness, right? Yes. So this will be a positive value. Be it ideal solution, non-ideal solution, it will always be a positive value. Okay. Yes, so you can write this here. Perfect. Very good, my dear students. This is how we talk about the negative deviation. So here are a few examples of negative deviation where the interactions after mixing become stronger. So you can go through these examples. These examples are important. If you know these examples, you are crystal clear. Don't worry about it. If you know these examples, you will be asked only these examples only. Okay, or something similar. So you can answer very easily. Now we have to draw the graph here. Let's draw the graph. I hope it's not very typical for you now. You will have to draw this, and then this time we'll draw for ideal solution first. This will be PA naught, and let's say this will be PB naught. Here, ma'am, XA will be equal to 1 and XB will be equal to 0. Here XA will be equal to 0 and XB will be equal to 1. We will join this here and we will join this here, and then we'll combine these two, right? You will combine these two. This is not a straight line. I'll draw a straight line. Okay, a straight line, and then we'll just a second, then a straight line. See, now you know that this is solutions vapor pressure if it followed Raoult's law, but it is showing negative deviation. This means that the vapor pressure is less than the expected. So the plot will be something like this. The plot will be something like this. The plot will be something like this. I hope it's clear. This is how you plot a graph for the negative deviation from Raoult's law. Okay. Yes, you can write this and then we'll move forward. Then we'll try to solve a few questions and then let's see. Okay, let's solve some questions. Here is the question. Question says that the mixture which follows positive deviation from Raoult's law. It was asked in 2020. Such easy questions, my dear students. Just see what does the question say. The mixture which shows positive deviation from Raoult's law. What is Raoult's law, my dear students, ma'am? Positive deviation from Raoult's law, the vapor pressure should be more than the expected. If the vapor pressure is more, this means that AB interaction should be lesser than AA interaction and BB interactions, right? Yes. Let's see, after mixing the interaction should become weaker. First option is benzene and toluene. It is an example of ideal solution. It is an example of ideal solution. Both are non-polar, right? So this is not your answer. Then you have acetone and chloroform, my dear students. Acetone and chloroform is the example of negative deviation. It is an example of negative deviation because here stronger bonding becomes after the solution. You have chloroethane and you have bromoethane. You have chloroethane and you have bromoethane, my dear student. It is an example of ideal solution. Again, nearly same interaction, so it is a ideal solution. You have ethanol and acetone. My dear students, ethanol and acetone individually have stronger bondings, interactions, and after mixing their interactions become weaker. That is why it is the example of positive deviation. And this will be your correct answer. So option D is your correct answer. So you just have to read the examples and you have to cancel out the options and you can find out your correct answer. So easy, right? Yes. So I hope you're clear with this concept. You can write this and then we'll move forward. Let's talk about the other question. You have the next question. The mixture that forms maximum boiling. Okay, we haven't done yet azeotropes. So azeotropes question we'll do later. So just leave this question and you will have to do this question now. Okay, try this question. Which of the following statements is correct regarding a solution of two components A and B exhibiting positive deviation from ideal solution? You have two components which are exhibiting positive deviation. Again, my dear students, if positive deviation means that AB interactions are weaker than AA interactions and BB interactions, right? Yes, and let's see one by one. First is intermolecular attractive forces between AA and BB are stronger than between AB interactions. Absolutely correct. This statement is correct. We just wrote it, right? Yes, you have to tell the statement is correct regarding. Okay, we've seen that it is correct. Now let's move forward and study more. Which of the following statements is correct regarding a solution of two components A and B exhibiting positive deviation? Okay. Second is delta H mixing is 0. Is delta H mixing 0 for positive deviation? No. For positive deviation, delta H mixing comes out to be positive. Right? Yes. So this is not correct. Delta V mixing 0? No. Delta V mixing also comes out to be positive. So this is also not correct. Intermolecular attractive forces between AA and BB are equal to those between AB. No, this is the case of ideal solution, not for a positive deviation. So this is also wrong. Only one statement is correct, which is option A. So option A is your correct answer. Right? Yes. I hope you're clear with this concept. Such an easy question. Perfect. Let's move forward to the next question. Next question is here. Can I give you this question as your homework, my dear students? All the NEET aspirants as well as JEE aspirants have to solve all the questions. I bring such questions which might be of JEE, but they are such questions which NEET students can absolutely do. Okay, so all the questions are for you, be it JEE, be it NEET. Try all of them. Okay, so this will be your homework question. Try to do this question yourself. Okay, perfect. It is something similar to the question we solved. Let's talk about the next question. Read the question very carefully. It is a very easy question. It seems like a very difficult question, very tricky question, but it is a very easy question. Let me tell you. Try this question. Okay. Two open beakers are containing a solvent and the other containing a mixture of that solvent with a non-volatile solute are together sealed in a container over time. You have to tell which of the following is the correct statement. You have to tell which of the following is a correct statement. Okay. So what does this? Okay. First, pause the video, try yourself and then see my approach. Okay. I hope you might have paused the video and answered. Now see. It says that you have a container which is pure solvent. Okay. Let's say you have a pure solvent and its vapor pressure is P1 naught. Then you have another container which is your solution which has a non-volatile solute to it. Let's say its vapor pressure is PS. This will be equal to P1 naught mole fraction of 1. Yes, because the solute is non-volatile. We started this lecture from this particular part, and we also know that P1 naught will be more than PS. Right? We know that P1 naught will be more than PS. This is the thing that we know. Now let's read the statements. The statement says that the volume of the solution decreases and the volume of the solvent increases. Okay, I didn't get it. Let's see. The volume. Okay, they are not asking us about the vapor pressures. They are actually talking to us about the volume. But we haven't studied anything about volume. How can we answer this question? We can answer this question very easily. Now you have to just understand this concept. You just have to understand this concept. Okay. Now, my dear students, you know that the vapor pressure of P1 naught is more than PS, right? This means that this pure solvent will form more of vapors as compared to the solution at the same temperature, right? If my dear students, this solvent is forming more vapors, this means that if more of the particles will go outside and form vapors, my dear students, its volume will start on decreasing because more of the particles are going, and since it is an open container, it is an open beaker. Since it is an open beaker, it will just move out. It will not come back, right? Yes, this is the tricky part here. This was only the tricky part here. You only had to understand that since more of the vapors will be formed in pure solvent as compared to this, more of the vapors will go out easily and its volume will decrease more fastly as compared to the solution. So at any point, if you see the volume at any temperature, if you see the volume, what will you say? That pure solvent's volume is less compared to the solvent's volume, compared to the volume of the solution. This means that we can say that volume of the solution is actually kind of increasing, because it is not actually increasing, but you have to answer accordingly, right? So you can understand this in this way, that because more of the particles will go into the vapor phase and its volume will decrease more as compared to this. So this will have more volume and this will have less volume. Okay, so now just read the top options and you will get your answer. The volume of the solution decreases and the volume of the solvent increases. No, this is not right. Solution's volume should increase, kind of, right? Yes, the volume of the solution does not change and the volume of the solvent decreases. Yes, the volume of the solution does not change and the volume of the solvent decreases. No. It actually changes, kind of. The volume of the solution also changes, right? Yes, it will also change, but comparatively less. Okay, so this can be our answer. Let's see. The volume of the solution increases and the volume of the solvent decreases. We can kind of say this part as well, right? Yes, so I think the C part will be your more absolute correct answer. The volume of the solution and the solvent does not change. This is absolutely wrong. So my dear students, here you have to answer this question as the volume of the solution increases and the volume of the solvent decreases, because you see that for the solution, though the vapors are forming, but they are comparatively lesser as compared to the pure solvent, and that is the reason we give the answer C and not B, because the volume of that actually changes. It actually changes. So if we see both of them, we'll feel like it's the solvent's volume is decreasing and the solution's volume is increasing. So option C will be your correct answer. I hope you can answer this question like this. Perfect. Let's move forward. Here you have today's last question, my dear students. It is also a JEE question. I think they forgot to mention it. It is a JEE question, my dear students. I don't remember the year, but still it is a JEE question, PYQ. So try to solve this question. Okay, what does the question say? The question says that the following interferences are made. Okay, you are given a plot and the following interferences were made. Let's see. Which of the following has higher intermolecular interaction compared to the other? That is how it is giving you. How are you going to calculate this? See, try yourself and then I'll help you out. Okay, answer that. I'll help you out. So you are given vapor pressure on the y-axis and you are given the temperature on the x-axis. Okay, I know that a component which is more volatile, that can form more of the vapors, right? Yes, ma'am, that can form more of the vapors. How can it form more of the vapors? Because its interaction might be weaker as compared to the others, right? So I can say that more the vapor pressure, lesser will be the interactions, less strong will be the interactions, right? We can say that. Now what will we do? What do we do? Let's, my dear students, fix this. Now I have fixed the vapor pressure. Okay. Now my dear students, imagine if the vapor pressure is 500, which component will achieve 500 vapor pressure faster at a lower temperature? A component which will be more volatile, that will have a tendency to form more of the vapors, and its vapor pressure will be equal to 500 more easily at a very low temperature. You can say that. Yes, see, at 293 this component had 500 mm of vapor pressure. At 313 this component had 500 mm of vapor pressure. Not 293. This component, just let me show you. This component had at somewhere here, but this component had somewhere here the vapor pressure equal to 500, and this component had somewhere here the vapor pressure. So the lowest temperature, where 500 mm of Hg vapor pressure was achieved was by x, y and z aren't written, I guess. This is your x, this is your y, and this is your z. Okay, yes. So x had 500 mm of vapor pressure at the lowest temperature. If it had the 500 mm of vapor pressure at the lowest temperature, this means that x is most volatile. So I can say that x is most volatile. X is most volatile, my dear students, then I can say that X will have the least interactions. X will have the least intermolecular interaction. That is the reason it was able to form vapors more easily, right? Yes. So X will have the least intermolecular forces of interaction. Now let's read. X has the higher intermolecular interactions compared to Y. It is wrong. X has less interactions, right? X has lower intermolecular interactions compared to Y. Yes, this is correct. Z has lower intermolecular interaction. See, Z was the one which had pressure equal to 500 at the highest temperature. So Z has the maximum intermolecular forces of interaction and Z is the least volatile. So this statement is wrong that Z has lower intermolecular interactions as compared to Y. Y had lesser intermolecular interactions as compared to Z. So here only one statement is correct, which is your A. So let's see which option is correct. A. Option C will be your correct answer. Option C will be your correct answer. This was a very tricky question. You just needed to understand the concept and solve this question. Okay, so if you are clear with the concepts, only then you can solve this particular question. Okay, so my dear students, today we'll only cover this much part. We'll cover the azeotrope part in the next lecture. It will take, I think, 10 to 15 minutes, don't worry, and then we'll move forward to our next topic. Okay, so I hope you were clear with the concepts today. I tried to cover every part and I tried to bring every PYQ based on those concepts so that you will gain some confidence. The most important key to excel in physical chemistry is only one, that is your practice. You need to practice every day and you need to gain confidence every day. If you trust yourself, you can do anything in the world. So just focus on your dreams, focus on your work and just work hard, my dear students. Then no one can take your goals away from you. So just keep working hard and make everyone feel proud. We'll meet in the next lecture. All the very best. Thank you so much.